This video will be about network cables and cable types. If you remember from the last video, we talked about what is Ethernet. Ethernet is a collection of network protocols and standards. And there are cable types based on those Ethernet standards. But why do we need to know these protocols and standards? Or why do we have a need for protocols and standards in Ethernet? So let's say you were trying to order a pepperoni pizza, but you were speaking English and the guy you were ordering from didn't understand English. You wouldn't be able to communicate with each other. For Ethernet, you're typically going to see what is called an RJ45 connection, as you see displayed in this switch or in this home router. Ethernet speeds is measured by bits per second. Bits are displayed by either a 0 or a 1. For example, viewing this YouTube video is nothing but a series of zeros and ones. So if a 0 and a 1 is a bit, what makes up a byte? Well, 8 bits equals 1 byte. So speed is measured by bits per second. So you need to think about all these ones and zeros going down the wire between devices. Going down the line 1 bit at a time, like this. It does not, however, go 1 byte at a time, similar to this. So remember, with Ethernet, speed is measured by bits per second, not bytes per second. For example, you have kilobits per second, megabits per second, or gigabits per second. And a gigabit is roughly 8 times the size of a bit. So to review some of the speeds that's available that you may see on the CCNA, 1 kilobit is 1,000 bits, 1 megabits is 1,000,000 bits, 1 gigabit is 1 billion bits, and 1 terabit is 1 trillion bits. But you probably won't see anything that fast on the CCNA or even in the wild, although Ethernet standards are getting faster all the time. Ethernet standards were defined in 1983 by the IEEE 802.3 standard. IEEE stands for the Institute of Electrical and Electronics Engineers. You'll notice that all Ethernet standards start with IEEE 802.3. So here's a simple table that shows some of the IEEE standards that you'll see in the CCNA exam. We have the common Ethernet speeds of 10 megabytes per second, 100 megabytes per second, 1 gigabyte per second, and 10 gigabytes per second. These are the common names that you'll normally hear in your work environment when talking about Ethernet speeds. For example, Ethernet, Fast Ethernet, Gigabit Ethernet, and 10 Gigabit Ethernet. Now here's the official IEEE standard associated with the cable. You probably won't use these very often when talking to other technicians when working, but it's important to know them for the CCNA exam. Next, I have the informal name that you'll often hear them referred to. For example, the 10 base T, 100 base T, 1000 base T, and 10G base T. The number refers to the speed. The base T refers to baseband signaling twisted pair, meaning they are copper Ethernet cables. You probably won't be asked what base stands for in the CCNA. I just added that in so that you would know what we're talking about in this video. Next is the max cable length. All of the copper Ethernet standards is 100 meters. I know that was a lot, but I do recommend that you memorize these Ethernet standards because more than likely you will get a test question related to them on the CCNA exam. The copper cables used in Ethernet standards are going to be UTP cables. UTP cable stands for unshielded twisted pair. Unshielded meaning no metallic shield around the wires, and twisted pair meaning 4 pairs of cables twisted together, which protects against electrical magnetic interference. If you look at this photo, you can see the 1, 2, 3, 4 pairs of twisted cables, and that's the twisted pair in the UTP. So if you look at this RJ45 connector from earlier, you can see 8 pins, which are the 8 cables total for the 4 twisted pairs. But not every Ethernet standard actually uses all 8 wires. For example, 10 base T and 100 base T uses 2 pairs, or 4 wires altogether. 1000 base T and 10G base T use 8 wires, or 4 pairs of twisted cables. So I'm going to focus on the 10 base T and 100 base T first. So let's say that we're going to connect a PC and a switch. That will be using wires 1 and 2 to transmit data from the PC, and the switch will be using wires 1 and 2 to receive data. They both will be using wires 3 and 6. The switch uses wires 3 and 6 to transmit data, and the PC uses wires 3 and 6 to receive data. This ability for the PC and the switch to send and receive data at the same time using 2 separate sets of wires is called full duplex. So the PC will send data on wires 1 and 2, and the switch will transmit data on 3 and 6. So the PC receives data on 3 and 6, and the switch receives data on 1 and 2. Let's switch the connection from a PC and a switch to a router and a switch. Just like the PC to switch, the router to switch connection will still use 2 twisted pairs using pins 1 and 2 and 3 and 6. The switch will receive on pins 1 and 2, and the switch will transmit on pins 3 and 6. And the router will transmit on pins 1 and 2, and the router will receive on pins 3 and 6. So again, the router transmits on pins 1 and 2, which is where the switch receives at on 1 and 2. And then the switch will transmit from pins 3 and 6 to where the router receives at on pins 3 and 6. And all this is what's called a straight-through cable, which means pins 1 and 2 go straight to each other and pins 3 and 6 go straight to each other. And because both a router and a switch uses full duplex, they can both send and receive data at the same time. Now, straight-through cable works great for 2 devices that are different, like a router to a switch or a switch to a PC. But what if you want to connect 2 similar devices, like a router to a router with a straight-through cable? If the router on the left was to try to send data to the router on the right, nothing would happen, because both routers are trying to transmit on the same pins. Now, if you switch out the 2 routers with 2 switches, the same thing is going to happen because they're both similar devices. The switch on the left tries to transmit data to the switch on the right. So as we've said before, a straight-through cable connects pin 1 to pin 1, pin 2 to pin 2, pin 3 to pin 3, and pin 6 to pin 6. But there is another kind of cable called a crossover cable. And in a crossover cable, pin 1 connects to pin 3, pin 2 connects to pin 6, pin 3 connects to pin 1, and pin 6 connects to pin 2. So the pins cross over each other, allowing 2 similar devices to both receive and transmit data. So now, even if looking at something like a router and a PC, which both transmit data on pins 1 and 2, and they both receive data on 3 and 6, you can use a crossover cable to connect pins 1 and 2 from the router to pins 3 and 6 on the PC, and pins 1 and 2 on the PC to pins 3 and 6 on the router. And the pins being able to cross over like this allows both devices to send and transmit data at the same time. Here's a chart showing some of the common devices you're going to see on a CCNA exam. A router transmits data on pins 1 and 2 and receives data on 3 and 6. Our firewall will transmit data on pins 1 and 2 and receive on pins 3 and 6. PC will transmit data on 1 and 2 and receive on 1 and 6. And a switch will transmit data on pins 3 and 6 and receive on 1 and 2. So if it helps you remember, a router, firewall, and PC will all transmit data on 1 and 2 and receive on 3 and 6. And a switch will be different and transmit on 3 and 6 and receive on pins 1 and 2. Well, that's very important to know for your CCNA exam. Most modern devices have a feature called Outtro MDI-X. With Outtro MDI-X, you can connect 2 devices such as 2 switches together using a straight-through cable, and Outtro MDI-X will automatically detect which pins are receiving data and which pins are transmitting data, and will internally switch the connection, enabling it to receive data from the other device and send data to the attached device, just as it normally would if you were connecting a switch to another piece of equipment. So while this is important information to know for the CCNA exam, unless you're working with a really old piece of equipment, in the wild you won't have to worry too much about a straight through or a crossover cable. So now once we move up to higher speed Ethernet cables, all 8 wires are going to be used. So one pair is going to be 1 and 2, a second pair is going to be 3 and 6, a third pair will be pins 4 and 5, and the fourth pair will be pins 7 and 8. So along with using all 4 pairs of cables, each cable is also bidirectional, meaning that each cable can both receive and transmit data, allowing them to operate at the much higher speeds that you see available. Now there is also fiber optic cable available, which is capable of far greater speeds than copper, and they can also go a longer distance. What you see over here is a fiber connection for a switch, and what you have is the fiber optic cable that connects up to these small form factor pluggable receivers that is plugged into the switch to the side of the RJ45 connectors you see. Here's the end of the fiber optic connector that actually plugs into the small form factor. They send light over glass fibers. One cable transmits and another cable receives. So if you remember from UTP cables, they use separate pins within the same cable to transmit and receive data. Whereas in fiber optic, you will use one cable to transfer and then one cable to receive, similar to this image here. And since they're able to transmit and receive at the same time using an individual cable, it makes them capable of much higher speeds. And similar to UTPs, the transfer on the left connects to the receive on the right, and the receive on the left connects to the transfer on the right. So if you were to actually look at the breakdown of the fiber cable itself, you have the fiberglass core that actually transmits data in the form of light from one device to the other. And then the core is surrounded by a cladding that helps reflect the light. Then you have a protective buffer that surrounds the cladding and the fiberglass core and helps keep it from breaking. And then you have the outer jacket of the cable itself. There are two main types of fiber cables out there. You have single mode fiber and multi-mode fiber. If you look at this example of multi-mode next to single mode fiber, multi-mode fiber, the core is wider, whereas in single it's narrower. The multi-mode fiber is capable of multiple modes or angles of light, whereas the single mode fiber just has the single angle of light. Multi-mode fiber is capable of carrying signals across a longer distance than UTP, but it's a shorter distance than single mode fiber. Single mode fiber is capable of transferring data over a longer distance than multi-mode fiber. Multi-mode fiber is usually constructed of cheaper transmitters when compared to a single mode fiber. Looking again at the single mode fiber diagram here, compared to the multi-mode fiber. Single mode fiber, the core is narrower. Light enters at a single angle from a laser. Single mode allows for longer cables than both UTP and multi-mode. The single mode fiber is usually more expensive than multi-mode fiber. Now here are a couple of the fiber optic standards out there. You have the 100 base LX, which is the IEEE standard 802.3Z, which is capable of 1 gigabytes per second, and it can be multi-mode or single mode, and the max length is 5 kilometers or 550 meters. You have a 100G base SR, which is the IEEE standard 802.3AE, which carries a speed of 10 gigabytes per second. It's multi-mode and can cover a 40 meter distance. You have the 10G base LR, which is 802.3AE, capable of speeds of 10 gigabytes. Is single mode fiber and can cover 10 kilometers. And you have the 10G base ER, which is IEEE 802.3AE standard, which can carry a speed of 10 gigabytes per second, is single mode, which can cover a distance of 30 kilometers. So I recommend making flashcards and at least being familiar with the basics of these standards before going into your CCNA exam. I'm going to round all this out by doing a quick comparison of UTP versus fiber. UTP is typically a lower cost. UTP has a shorter maximum distance. UTP is vulnerable to EMI. RJ45 ports and connectors are cheaper, and UTP's cabling emits a faint signal from the cable. Now, fiber cables cost more. They have a longer maximum distance. Fiber cables are not vulnerable to EMIs. The small form pluggable ports for fiber cables are expensive compared to the RJ45 connectors. Fiber cables do not emit any signal from the cable, so in theory that makes them less of a security risk. Thank you for watching. If you found this video helpful, please be sure to hit the like and bell icon to subscribe and be alerted the next time a new video comes out. And feel free to share this video with anybody you think would find it useful. If you have any comments, feel free to leave them down below, or you can go to my website and reach out to me through there. My website will be listed below, along with a link to this PowerPoint presentation you saw.